So let us start again the design of reinforced concrete structures. So far we have done that beam, we have done beams, design of beams, then we have done slabs. Now we shall come to the columns, that compression members. Next we shall go for footing. In addition to that, we shall also design staircase. So if we can design all those 5 components, we shall be able to design a building. That is our primary concern, at least for this particular course. We can have advanced one, say silo, then bunker, then your say water tank, so many other components, but anyway finally you will come back to these components where these beams means flexure and shear. These are the dominant one. We can have say axial one also, we can have torsion also, that we shall consider. So what are the basic 4 components? One is that flexure, then we have shear, axial, and then we have torsion. So if we find out all 4 will not act in any particular element. Elements means here we are talking say beam, slabs, columns, footing, staircase. These are all calling say module or elements of a particular building, of a particular structure. It may be bridge also. There also you will find out few of them like that, beam, slabs, columns, like that you will get it, as well as footing also. The footing will be different. For building, whatever the type of footing, for bridges the footing will be different. Generally we call it say piers. Piers are supported over the piles. So we have to design your say piles. Over that you are having pile cap, then over that you are having piers, finally you are having that say pier cap, then you are having bearing, and over bearing that your superstructure will be that set. So this is the different components for bridges. For buildings here, whatever we shall do, we shall start from the top, say slab, then your beam, then your say what is called columns. Finally the load is transferred to footing, so we have to design footing. In addition to that, for access to the different floors, we have to design staircase. But all those things you will find out here, flexure and shear in beams, I shall show you at least one problem where the torsion also may act. So if torsion is there, then how to tackle that type of beam problem? So where it may work like this, say for example, this is the one case of beam. Now due to this load, what will happen? This beam subjected to the torsion. Not only a beam which is bending like this, as well as it can, if it bends the other way, that means along this one, so that also you have to consider, and how to design that when torsion is applied. So that we shall find out, that one let us consider for the time being, say little we say advanced stage, but anyway we shall find out. Slabs mainly we have found it is nothing but flexure. So in few books you may find that they have started with the slabs because it is a flexure one, then flexure and shear. Here we shall come the columns, axial force, and also it may occur that it may happen that moments also applied, bending moments also applied. So we can have this type of problem. Then footing is nothing but extension of column. So here also we can have axial and moments. Staircase, when we are considering here, most of the cases, common staircases, we generally consider it as dominant one, predominant one, that flexure. So we have to design staircase, that we shall take it separately. What I mean to say here, all the components, that means if you take it say one component wise, and if we consider the superposition valid, because independently we are working. So flexure, shear, flexure, axial, bending moment, all those things are working, and torsion also can work. So that's why we are considering this one as a say element wise, different elements. So whenever you are considering one particular structure, then you have to find out what are the different elements and what are the forces acting, which one is dominated. Whether bending moment, then you have to take care in a certain way, because that you know. Whether it is a shear, that you have to take care in that direction. So like that you have to go. So here today, we shall in next few classes, we shall consider say your columns. Columns, if we consider, so if we consider that columns, so let us start. We are starting here today that one say lecture 19. So design of columns part 1 that we are talking. So let us see first, already I have shown, but let us come here specifically that this is your beam reinforcement. You see this is the top of the, this is slab, this one is your slab, the reinforcement, and you are providing this one. You please note these all those things provided here to give clear cover, because otherwise it will just simply lie on the that your say floor itself, floor of that say this formwork. So you will not get the clear cover. So you have to provide that clear cover here, here, like that. You have in different places you have to give that clear cover. Now you also see this bar. If you just reduce the, subtract the clear cover from the top of the slab or from the floor, you will get this one, that is at the top level. So that means here you can consider that is T-beam, that designed as a T-beam. So if we, what I mean to say, this is your say slab, this is your beam, let us say. So your reinforcement is going up to this for beams, and here whatever your reinforcement for the slab, that is also there. It's not that we are not truncating here, because it will be cast monolithically with the slab also. So, and you can see few places there is a lapping, big one, small one, all those things. What you have to do when you are talking say reinforced concrete, you have to consider also what gaps should be provided here, these gaps. That also you have to, because whenever you are giving the detailing, reinforcement detailing, that time also you have to consider, they have to take care that whether you are having sufficient gap for providing your say coarse aggregates, because it is dependent on the coarse aggregates. Otherwise what will happen at the time of casting, if proper vibration is not done, then it may happen there is a gap. There will say the material that one, there is a void in the concrete, and which will weaken the concrete, though you have designed for say M20 grade of concrete, but even then you will not be able to achieve that particular one because of these voids. So that's why it is very, very important also that you have to check whether you are having sufficient gap and how much will be gap, because if you consider say maximum size of the aggregate, so 20 millimeter, if it is 20 millimeter, so at least you have to provide that 20 millimeter so that one coarse aggregate can be accommodated within that place. So like that, that our code says in detail, that we shall come afterwards when we shall come in detailing one. Anyway, so another one here very important, though we are providing say 4 bars, let us say we are providing 4 bars in the column in 4 corners of a rectangular column. Similarly, how many bars you have to provide for say circular one? Code says that you have to provide 6 numbers. For rectangular one, 4 numbers minimum, and for circular one, 6 numbers that you have to provide. Now, what is the bar diameter? What is the minimum bar diameter? Because these all those things you have to give detailing, that one you have to provide. Now, when you are talking this one, that how many bars, that means what is the minimum percentage of steel of the cross sectional area? If B and D is the, that is the, always you have to take care that portion. That part always you have to take care, and our code says say for example for slab it is 0.12% for HOISD or deformed bar. whereas 0.15% for the that you would say just mild steel. So that is for slab. Similarly for columns also we have certain kind of minimum reinforcement that you have to provide. Even if you do not have that say sufficient strength that load applied, even then you have to provide that minimum. Similarly, that what should be the minimum dimension, that there is a restriction also. That means you cannot go less than that value. Generally we provide say 200 millimeter. So these all those things you have to provide. So first of all, the load is applied. In our case it is just simply say axially loaded one. It is axially loaded for the time being say consider. But even then, even if it is not axially loaded, say for example, if this is a column cross section, I am talking the plan. So how far shall we allow? It is the ideal case. That means the load is applied here, that axially loaded. This is a very, but that is not possible. Even if you go from the first floor, ground floor to the top floor, maybe say second floor or third floor level, then even then due to construction also it will deviate little bit. So how far shall we allow this eccentricity? And how far shall we allow so that we can say it is, though it is theoretically not, but practically it is an axially loaded column. Otherwise what you have to consider? Otherwise you have to consider this one here, that moment also. In addition to the load, that moment also you have to consider. So if we, let us consider before going to detail, when you are talking say your column, what we have, what are the different components we have to provide. So we have to provide, so let us first jot down columns. We can have the dimension, the rectangular, square also one special case, circular, let us keep that one say square. It can be hexagonal also, or it may be any other shape from the other point of view, maybe architectural point of view or from practical point of view. That also you have to consider. It may happen that the shape could be like this also. So like that, or the shape, because we do not know that all, there could be many other shapes, so that means I can provide the shape like this also. Sorry. So in this way the different shape also possible, but what we have to do, that we have to design this one. Number 2, that you have to provide that minimum reinforcement, minimum number of bars. Minimum number of bars. We have two, one is called longitudinal, this is called also main reinforcement, or so this main reinforcement, that is longitudinal, mean here this one, we call this one called longitudinal. So when we talk this one, that means this one will share the load along with the concrete. Concrete and steel both together will share the load, and that one will be shared by this longitudinal one. Then we are having say minimum reinforcement. Minimum bar diameter. Both for main and transverse. Spacing of bars. And spacing of bars, there is one more we call it, that is that main and transverse reinforcement. So let us give that one say transverse reinforcement here, let us provide here. So this transparency we call it tie verse. The compared to that your say stirrups, here we call it tie. So tie means this is the lateral reinforcement. This is the lateral reinforcement that you have to provide, or I can say this one. So this is your that ties we are providing here. Personally I don't like this type of say one. Generally we provide whatever the gap instead of providing here, I prefer say one along this, the other one little gap here, that I shall tell you in due course. That will be easier to make it, because anyway, but this is that is it, but it is also correct, but it depends on that how fast you can say make the workmanship that work. That's why we can put it other way. So detailing also, it is not the unique solution. You can have number of solutions also. And this is your say one circular column and with spiral. That means not only you can provide ties, but also you can provide that one say a spiral binding like this, it can go. Okay. So when we come to this one, these are the different components that we have to provide. In addition to that, we have, when we consider these all of them, so these columns, say dimension, then you say minimum number of bars, minimum reinforcement, all those things, the transverse reinforcement, all those things we have. In addition to that, we have to take care that what is the effective length of the column. So from there also you have to find out what is that, whether it is a short column or long or slender column. Long or slender column. Let us come to the one that definition of column. There is one more item, we call it pedestal. Pedestal, that is just a simple one, a short one, and it is having say certain kind of say dimension. If you take the pedestal, you are using for some purpose, maybe for say for machine foundation or maybe different purpose, you are using certain kind of pedestal we used to make it. Now we are calling this one as a pedestal. Shall we call it say your why not columns also, because it is having also axially loaded, or even if it can have say bending also. The code says, and that we shall find out here, the code says, let us come to the clause, specific clause, because that is very, very important. Okay. I think I should say, anyway, I think 25.1.2, 25. Yes. So we can get this one in clause 25.1.1, page 41, IS 456 2000. Our code says the column or strut is a compression member, the effective length of which exceeds 3 times the least lateral dimension. Effective length greater than 3 times of least lateral dimension. Please note least lateral dimension. That means if it is a rectangular one, generally we provide this one say your B. and the other one say your D, depth, this is width. Generally it happens that this is the width always is smaller compared to the depth. So effective length should be greater than 3 times of the least lateral dimension. If that be the case, then only we shall consider this one as a column. Otherwise, it is a, say here in this case the pedestal, so it is dependent on this one. So if it is less than equal to that less than 3 times say your least lateral dimension, then we shall consider it as a pedestal. Otherwise, it is a column. Okay. So what is short column? Short column here, Lex by D and the other axis Ly by B, say we are talking a section B and D. So if we take care this one, so Lex by D and Ley by B less than 12, then we shall call that one as a short column. Otherwise, it is a slender column. If it is greater than, so Lex by D and Ly by D be greater than, so then we have to take care that one is a slender column. For that, what you have to do, yes. Lex and Ly is the effective length x axis, about x axis, and effective length about y axis. So why we are having 2? Because we do not know the effective length of the column is dependent on the support condition. Effective length of the column is dependent on the support conditions. That's why your effective length could be different about 2 different axes. About x and about y it could be different. What is the support condition? The support condition could be, we are talking say at the bottom, at the top, support condition could be, it could be fixed here. We can get this one in IS 456 Annex E. We shall take care this one. So Annex E table 28. Annex E table 28 that we have, and we have how many different cases it says? It says 1, 2, 3, 4, 5, 6, 7. There are 7 cases. So let us first, since we are talking this one, let us summarize the whole thing. So table 28, it says degree of end restraint of compression members, and we can have case 1 effectively held in position and restrained against rotation in both ends. Effectively held in position and restrained against rotation in both ends. What does it mean? it means it is fixed at top as well as at the bottom. Effectively held in position, that means there is no lateral movement and restraints against rotation, so there is no rotation. So if that be the case, our code, we can find out the theoretical value and recommended code, what our code says. These are all for effective length. Where we shall get it? Table 28, Annex E, page 94, IS 456 2000. This is the specific reference where from I am talking. So effective length, then we are having theoretical value. What is the theoretical value? That we can get it as 0.5. I hope that you have done that column buckling in your third semester in solid mechanics. Those of you have done, at least civil engineering students, you have done it. So 0.5 L, you can consult Srinath also. Those you have not done it, so you can consult Srinath also. What I mean to say that here, because it is not in the scope, it will be difficult for me to continue to go to that level. So 0.5 L is the effective length, the theoretical value, but our code says that you take 0.65 L. We have this is your say fixed one, fixed case. We can have, so it means here, if I go back to the previous one, it means the effective length should be that if it is fixed, then we have to find out suitably that LEX and LY from the length whatever given. We can find out LEX and LUI, and then we can divide by the D. That means in other way it will govern us to find out the D also, because if we know the LEX effective length, then we can find out what should be the dimension. The minimum dimension we have to provide 200. Now we can find out if we would like to design it as a say short column, then we know 12. So on the basis of that we can find out what is the depth and width of that say your column. But if you have to design for say long column, sometimes we do it. In few cases you can find out say possibly in our institute those front that column 6 columns, those are your say if you get the dimension, those you will find out as you say your long column. So similarly that if you other cases say if you need that big headway possibly for your say for truck or any other loading unloading, so there you have to make it say long column, because there is no other way. So that's why we do it. It is not always possible to make it a short column, but mainly for buildings others we always provide say short columns. Sometimes it happens that your one column that is extended up to say your up to second floor level, not up to the first floor level, there is a gap, so then it becomes say your say long column. So now you know that what is that effective length. So let us complete this one then, what are the different other cases. So number 2, case number 2, effectively held in position at both ends, restrained against rotation at one end. Effectively held in position at both ends, there is no lateral movement, but only in one end it is restrained against rotation. That means one end fixed, another end hinged. That is the case what specifically it is telling. So I can say this is your say fixed case and this is your say hinge one. So if that be the case, we should have theoretical value and recommended value. So theoretical value 0.7 L and recommended value 0.8 L. What is this L? This L is the unsupported length. This L is the unsupported length. But even then our code says specifically that what does it mean, that what do you mean by unsupported length, that is also available. So that also you can get it specifically in clause. I hope, let me tell you here then, because all the things should be clear that what we are talking. So unsupported length, let me write down here, unsupported length L, L unsupported length. And you will get it in clause 25.1.3 IS 456. Let us give the page number also, page 42, IS 456-2000. You will get this one, specifically that one, say unsupported length in this clause. Let me just give you one example. There are so many cases in beam and slab construction. In beam and slab construction, it shall be that unsupported length shall be the clear distance between the floor and the underside of the shallower beam framing into the columns in each direction at the next higher floor level. So that code says actually underside the shallower beam that you have to take. Not that there is a, it may have that two, there are in two directions they are having two beams not having the same depth, so you have to take the shallower one, that means the depth less, so that one you have to take. So there are so many other cases also that you can find out in the clause 25.1.3, you can find, but anyway that you can find out here. So now if you come the next one, that number 3, it says that effectively, let us write down here, effectively held in position at both ends but not restrained against rotation. So this is a case of effectively held in position at both ends but not resistance against rotation. It is a case of hinge, both sides hinged. It is a case of both sides hinged. So it says you take it 1L, that means just simply you take it the unsupported length. So this is the case 3. So we have few more cases. Number 4, effectively held in position and restrained against rotation at one end and at other end restrained against rotation but not held in position. Effectively held in position and resistance against rotation at one end and at other end resistance against rotation but not held in position. It means as if you are having something like this. What happens here, in this case, it may move say like this. That means it can go, but there is no rotation. There is a roller here, you can consider here that particular one. It can move like this, but there is no rotation here. In that case, the theoretical value, it comes 1L, and recommended value, code says you take it 1.2L. So you have to take it, say recommended value 1.2L, that you have to take. So this is your another case that you have to consider. So we have 3 more cases. Let us finish that one, because you need for any case effectively held in position and restrained against in one end. That means one end again fixed, and at the other partially restrained against rotation, but not held in position. So effectively held in position and restrained against rotation in one end, that means it is fixed, and at the other end, other partially restrained against rotation but not held in position. So it is not fully restrained against rotation. So if that be the case, it is similar type, but we can have some kind of rotation here. If we look this one, that it can move only, so there is no that rotation here, but here we are allowing little bit that rotation. So if that be the case, then your theoretical value, there is no such thing that because you don't know how much is the partial one, but your recommended one, it says that you take it 1.5L. Basically what you are doing, you are moving towards that cantilever column. Basically you are moving towards cantilever column. You have started with the fixed one, we have started with the fixed both ends, then you have made one end hinged, the other end also hinged. Now you are coming to this one, that other end you are keeping always fixed, the top one slowly you are releasing. So it is already released from the your movement, but now you are releasing that you would say rotation also. So it is partially. So in that case you have to take 1.5L. Sixth one, that effectively held in position the same way at one end, but not restrained that means it is hinged, not restrained against rotation, and at the other end restrained against rotation but not held in position. So we are talking this way, and we can say it may be something like this. That means it can move and this side is hinged. So if that be the case, the theoretical value, it is 2.2L, and recommended value also 2L. So that is 2L is the maximum. So this is another case. Here this side is hinged. The other one we have considered this side is fixed. Here we have considered this side is hinged. So we can have that both theoretical and recommended at 2L. So that you have to take that you say effective length as 2L. The last one, it is nothing but the cantilever column, but we specify like this: effectively held in position and restrained against rotation at one end, but not held in position nor restrained against rotation at the other end. This is the maximum we can have. So we are talking like this, as if it goes like this. There is no such limit, neither in the your movement or in rotation. Your theoretical value, it gives 2L, recommended value, it gives also 2L. So this is the maximum we can have, 2L, that means twice the unsupported length, that is the maximum for the cantilever beam, and minimum, that is you say 0.5L. So it is very, very important that what should be the effective length. So this is the general case. Also we can also find out, because say if it is a framed structure, then how shall we find out the you would say effective length if it goes like this. So in that case also we can find out the stiffness, and we are having two more figures in that code. I think we shall come in due course when we shall solve that multi-storied frame, design that one. That time I shall tell you that how to find out that your say effective length for frame structure, that we shall find out, because you have to find out the stiffness, and on the basis of that at the top and at the bottom, from there we can find out the fixity level, and then we can find out that effective length. Okay. So that we shall do it separately. Here that we shall find out for say frame structures, that we shall do it separately. We are not going in detail. Anyway, so we know that effective length, that what does it mean, and it is very, very important. Now let us come, okay, these are the few cases already I have seen in the very beginning. So now we shall come to that one, that what is the method. The method is that here the same one we are talking is a limit state method, and this is limit state of collapse, not the serviceability. We are talking limit state of collapse. From the strength point of view we are talking that how much maximum load it can take, and this one we are talking compression. So far we have done your say shear, and we have done for flexure. Now we are talking say your compression. So for this compression, therefore one, what are the assumptions, because it is based on some assumptions, few assumptions. The assumptions of limit state of collapse flexure are valid, here also valid, those clauses are valid. What are those? That plane sections normal to the axis remain plane after bending. Maximum strain in concrete at the outermost compression fiber is taken as 0.0035. So that is the limiting strain for concrete. The tensile strength of the concrete is ignored. Just let us recapitulate once more. The stress block may be assumed to be rectangle, trapezoid, parabola, or any other shape which results in prediction of strength in substantial agreement with the results of test. This is the one that already we have taken care of, that which type of say your stress block we have to use. The stresses in the reinforcement are derived from representative stress strain curve for the type of steel used. For different steel we have to use different your stress strain curve, and the maximum strain is dependent on the steel used. So from there we can find out the maximum strain, that for say Fe 405 or Fe 250 or Fe 500 we shall get different limiting strain for steel. Now specifically for limit state of collapse compression, in addition to those, the maximum compression strain in concrete in axial compression is taken as 0.002. That means we are talking that 0.0035, that one, that limiting strain, that is from the bending point of view. For beam or slab we are taking 0.0035, okay. But here for direct compression we shall take 0.002, okay. So we shall take 0.002. That means if there is a column here, if you take a cross section, then we can have the strain 0.002, that is strain. The stress, what will be the corresponding stress? The corresponding stress here, because your stress block, it goes like this. The stress block goes like this. That means 0, somewhere here 0.002, 0.0035, and what about the design stress? This one 0.45 FCK. 0.45 FCK is the design stress that we have to accept it. After that partial safety factor, a lot of other things, that twice you are doing, then you are getting 0.45 FCK, which is nothing but 4/9 of FCK. So if you take, since you are allowing say 0.002, that is the limiting strain for direct compression, that means already you have reached up to 0.45 FCK. You have already reached up to 0.45 FCK. That means here you are taking the maximum stress allowable here. So this is your code says that maximum compression strain, that one you can use it here. Now the maximum compressive strain at the highly compressed extreme fiber, if we, let us read it because this is very, very important. The maximum compressive strain at the highly compressed extreme fiber in concrete subjected to axial compression and bending, subjected to, please note, axial compression and bending. The first one I have told, that is direct compression, only axial load, where we are limiting strain 0.002 and the stress will be 0.45 FCK. But here subjected to axial compression and bending, and when there is no tension on the section, that means no tension is developed on the section, in that case shall be 0.0035 minus 0.75 times the strain at the least compressed fiber. There is one maximum compressed fiber in one end, the other end, that is the least compressed fiber. So what does it mean? Let me explain. We say, if this is your say section, if this is your section, let us say D, if this is your section D, what we can do, okay, I think I shall I shall tell you in the next class, because it will take some time. Anyway, I shall tell you this particular one because it is very, very important, and it is very, very important for say calculation of say your, when you are talking say not only you are having axially loaded one, we have basically we have one case. I shall come in detail this particular clause. It is very, very important so that you can generate your own many things when you are talking say computer aided say design. So this is very, very important one, and we can do it for different purpose also. So one is that axially loaded. Number two, we can have that is called uniaxial bending. That means we are having axial load here, just simply axial load and say moment mx. This is a P and this is your say P and mx. The other one, it can be Pmx or Pmy, but when we talk this one, that means always I can take that one as x. So that's why when you are talking that one about x, so it does not mean that it can be about x about y, because if we take the other way, so that side still we can take it as say x also. And another one, it is possible say biaxial. So axial loaded, uniaxial bending, and we have biaxial bending. So these are the three possible cases, and you have to design for all of them. And so that's why it is very, very important, because this one, that strain, this particular clause, that assumption will give us that what is the limiting stress, and on the basis of that we have to find out. Okay. So let us stop here, then we shall continue in detail in the next class.